Hey, what's up, Mr. Baldwin and Miss Awad?
Hey guys, how you doing?
We're kind of in an uncomfortable position here, so you're not going to see much of our faces during this segment, but you're going to see a lot of our hands and a lot of these really great minerals. So, hey, and we'll be talking at you and showing you some things here. So here we go.
So we have to start with our silica challenge, right?
That's a good idea.
Okay, so we have to try and make it so we get all four of these styrofoam balls to touch each other at the same time, right?
Okay, so these are representing
These are our oxygens,
oxygen
right?
atoms. Okay.
And so we can use the toothpicks as bonds.
Okay.
And do we want to add the gummy?
The gummy is going to represent our silicon atom.
Silicon, yeah.
Excellent.
Okay,
Right.
so we have to make it so all four of these oxygens are touching and the silicon is touching all of them, right?
And the distance between the centers of the oxygens need to be equal.
Have to be the same.
Yes.
So, okay.
All right, so let's go ahead and make our structures.
I feel like I'm building a snowman.
It's winter, but it's not that cold yet. All right, so the way I have this set up right now, I've got 3 oxygens, and the centers are equal distances apart.
Okay.
And we're going to call this our basal unit.
Okay.
All right, so
So
it kind of sits on that nice firm base.
It's like the bottom of a pyramid almost.
Exactly.
Okay.
I'm going to go ahead and put the silicone in the middle.
Oh yeah. Looks like a nice place to rest.
It does. Sleepy bear.
And then our last one just goes right on top, right?
Okay.
And we're kind of squishing in our silicon there.
So this oxygen atom on the top is called our apex, or top. Like
Apex.
the apex predator, the top predator,
Nice.
the apex oxygen.
Okay.
So we can see that there's an equal distance between the center of the apex oxygen and each of the basal oxygens.
Mm-hmm.
Same distance between the basal oxygen centers.
Okay.
And that silicone atom is sandwiched in between, so the bond length, this is all held together by bonds, right?
Yeah.
The bond length would be equal between the oxygens and the silicone.
And so this is almost like a perfect structure here because everything is equidistant from the oxygen atoms, right?
Yeah.
Okay.
The only one big problem with this structure we need to take a look at
Mm-hmm.
is we need to take a look at the charge.
Oh, okay.
Right? So we have that concern. So let's look at it this way. We have one silicone atom, and the charge on our one silicone atom is a +4.
Mm-hmm.
And we have 4 oxygen atoms, and the charge on each one of those is -2.
Yeah.
So 4 times -2 is
Minus
a -8.
Yeah.
So we have a net charge here of a -4.
Okay, so this is going to be then an anion for the whole thing, right?
Yes.
Okay.
So while it looks like a great structure, and
Mhm.
it looks nice and steady there, stable, it has a problem in that it's looking for,
It needs some partners.
it needs a +4,
It
right?
needs some positives to
Yeah.
kind of connect with.
Right.
Okay.
So remembering that this is all happening inside a magma chamber,
Mm-hmm.
and these atoms have been bouncing off of each other because it's very hot.
Okay.
So they're starting to cool down. They're
Mhm.
becoming less energetic as they cool down, and these bonds are forming. So it's looking for somebody to partner with.
Okay. So.
And
Oh, go ahead.
well, what I was going to say is inside that magma chamber, we have some other things. Like we've got calcium and sodium and iron and magnesium
Mm-hmm.
and aluminum and potassium in addition to the silicon and the oxygen.
Okay.
Those 8 elements.
So it can probably grab some of these elements and start making bonds with those and probably start making some of our earlier minerals that cool at the highest temperatures, right?
Mhm.
Or crystallize at the highest
Yeah.
temperatures. So I see you've got the charges in there, and I've got some +1s, +3, +2, +2. Those +2s probably make sense, right?
So I think if we find an iron and a magnesium,
Okay.
or 2 irons or
Okay.
2 magnesium atoms floating around someplace,
Mm-hmm.
that we could satisfy that charge imbalance here.
Yeah.
And at that point, we would also form our first mineral.
Nice. Okay. And as I look at our chart here, if we look at our mineral formula, we've got our olivine.
Mm-hmm.
And olivine's got that magnesium and the iron, and it's got 2 of them. It's got a subscript of 2.
Right.
And it's got that silica tetrahedron there, the SiO4.
Yeah. So students, the chart that we're looking at here is in your textbook on page 96. And you should actually have this already in your notes, but if you don't, you want to take a look. You might want to make some notes there, or a separate piece of paper will work too for this. So let's bring out, why don't you show that sample of olivine?
So here's our olivine. It was one of those dark green ones that we had. And is it green? I mean, why is it green on this?
Olivine is always green, and it's really nice because you can remember olivine and green olives.
Oh,
so
nice.
it's pretty easy to remember that
Gotcha,
way, right?
cool.
Yeah.
Okay, so this is one of the first things that crystallizes then, because it's just a simple structure that we have. We've got this basic silicon tetrahedron, and it's combining with the iron and the magnesium.
Good.
Okay?
Okay. So this is all still floating around in that magma chamber. Now we have some of these solid crystals of olivine in the magma chamber. And those crystals are pretty heavy. They're pretty dense compared to the magma that they're floating around in. So they're headed
sink
for the bottom.
Yep.
So that's going to be a cumulate layer forming at the bottom of magma chambers, and we do see that a lot.
So at the bottom of a magma chamber, you'd find a bunch of olivine.
Find a nice layer of olivine there.
Cool.
Yeah.
Okay.
Good. But there are still some of those crystals that are floating around in the melt.
Okay.
And still some tetrahedra that are floating around in the melt.
Mm-hmm.
But we've also removed some of the silicone. We've removed some of the oxygen.
Okay.
We removed some of the magnesium and the iron.
Uh-huh.
So you can think about it as being depleted. It's like if you were eating a bowl of cereal like Lucky Charms.
Oh, I love Lucky Charms.
And you picked out all the marshmallows.
Oh, that'd be terrible.
Then your cereal bowl would only have milk and those other little
stuff.
Circles, right? But none of the good marshmallows.
Yeah.
All right. So now our magma has less iron and magnesium, just like our cereal had less marshmallows because we took them out.
Okay, and it's
Right.
not like we added anything else to it.
No.
We just took away some of it, and that increased our concentration of all the other stuff.
Correct.
Okay.
So when these are floating around, they may bump into each other. And because now we're dealing with efficiency, it's possible that we could use one less oxygen atom
Oh, and
by
combine them.
sharing like that.
Okay.
So this extra oxygen can go away and bond with something else.
Okay.
And now we have a second structure,
Okay.
and now it's made up of, let's see, I see
1, 2, 3, 4, 5, 6, 7.
Seven.
So 7 oxygens to our 2 silicons.
right.
Okay.
So Si2O7.
Gotcha. Okay. So that changes probably the charge then in there, right?
It
Okay.
changes the charge, but there are some minerals that form with that Si2O7 structure.
Okay.
So now if you can imagine a bunch of those floating around together,
Okay.
that they could combine, and what would end up happening, so let's go to some of these bigger guys here.
Yeah.
It'll be easier to see. Again, we've got our 3 basal oxygens on the bottom, and the apex oxygen here is pointing up. And then if we were to share one of our basal oxygens,
Oh, whoops. This next one would have to kind of be flipped upside down, right?
yep.
Okay.
So now we have a structure where we still have 7 oxygens and 2 silicones.
Okay.
But the oxygens, the apex oxygen is pointing up on the first one, it's pointing down on the second one, and we could continue to add additional ones off of here and make a long chain,
Uh-huh.
a long single chain. And here we're using our oxygen much more efficiently.
And this one would be then pointing up on the next one, right?
That one would point up, the next one would point down. So we get these long chains with thousands of these units.
Okay.
And those tend to attract iron and magnesium again.
Okay, yeah.
So what's our next mineral that we're going to be forming then in that structure?
Okay, so with this structure, we're going to have those pyroxenes, right?
Great.
Okay, so we're going to have our pyroxene group, and it's going to be this mineral right here that we saw during that mineral ID that we did the other week. And I see if you look at the mineral formula, they've got that magnesium still and that iron still in it. Okay.
So it's interesting to note, this is a dark colored mineral, iron and magnesium, that's where the ferromagnesium minerals comes from.
Gotcha.
And those are going to be the minerals we're going to find in mafic rocks.
Okay.
Okay, great. Now, we probably should draw this in a little bit more simple way because
I love drawing, yeah.
Yeah, it's kind of hard to look at these more complex drawings. So the way I like to draw this is to make a single silicon oxygen tetrahedron.
Okay.
I like to represent that by a triangle
Okay.
where each of the corners represents one of the basal oxygens.
Okay.
And then I like to draw in the apex oxygen as this corner or this top point here.
Okay.
So if you want to bring the structure back over.
So it's kind of like you're drawing it just like that. So
Exactly.
you're looking at it from above.
So here is this point, which is this basal oxygen.
Mhm.
This point is this one.
Mhm.
This point is this one, and the apex oxygen is here.
Right on the top.
And the silicone is sandwiched in the middle, right?
And we don't draw that. That would just get too crazy.
You're right.
Okay.
Okay. So that's how I would draw a single one. And then if I'm thinking about a whole chain, I'm going to show you the easy way to do this.
Okay,
I'm
that's
going
a lot
to
of
draw a
triangles.
line, and then I'm just going to zigzag triangles above the
Nice.
line and below the line, and above the line and below the line. And this is how I'm going to represent my single chain or my pyroxene structure.
Okay.
And I'm going to alternate between the oxygen pointing up and down
Mhm.
by using a dashed line when it's pointing down and a solid line when it's pointing up.
Okay.
Okay. So here's olivine,
Okay.
which I'm going to abbreviate OL. Do you do that too?
I am going to now. That's awesome.
And pyroxene, which I'm going to abbreviate PX.
Nice. Cool.
Okay?
Okay.
So, what do you think happens next? We've got these chains floating around in the magma.
So there's a bunch of chains. They can start connecting probably to each other, and I'm
Mhm.
guessing not end to end. They're going to start adding chains side by side.
Yeah.
Cool.
So here's where they're going to share, right?
Oh, okay. So they're going to be doing off those basal oxygens. They're
Yeah.
going to be adding other chains.
Right.
Kind of connecting to them.
Right.
Okay.
Good. How do you think we're going to draw that?
I'm thinking a lot of zigzag lines now.
You want to try it?
Yes,
All
I
right.
do.
Go ahead.
Okay. So I'm thinking I'm going to draw mine over here.
Good.
So I draw my first single chain, and I'm going to draw it just like I did my zigzags before. My zigzags are okay. And then I need another chain. Oh, I got to do my middle part. That one's up. This one's down. This one's back up again. And then this part looks tricky, but I'm going to do another chain over here. And I need this one to connect to it right here.
Perfect.
And it's not quite, the same,
That's
but
close
enough. Okay, we're not in art class. Now, if this one's going down, next one's got to be going up, right?
Mhm.
Okay? So it's going to look something like that.
Mm-hmm.
And then if this one's up, then this one's down.
Right.
Same thing over here.
Yep.
And then even if I wanted to get crazy, I could extend this way.
Exactly. Thousands of atoms long.
And this goes on like long
Yeah.
chains, yeah.
So the advantage of this is that now you're sharing
Mm-hmm.
each of the basal oxygens
Mm-hmm.
are being shared.
Okay.
Every basal oxygen would be shared.
Because sharing is just a fantastic thing to do.
Sharing is caring. Right?
Yeah.
You got it. All right, so in that case, which mineral group have we built here?
Oh, so we got a double chain. So if I look at my picture here, I've got a double chain here, and this is my amphibole group. So
Good.
like my hornblende, the amphiboles.
Yeah.
And if we look at an actual mineral, I'm still a black one, right? I'm still dark.
Yep.
Okay?
Does that make sense with what's in that mineral?
Well, if I look at the formula, I've got a little bit of calcium now, but I've still got a lot of iron and magnesium. So it's dark because it's still got that iron and magnesium in it, right?
Yep.
Okay, good.
Perfect. All right,
Probably going to get crazier now, right?
you're right.
Because I've got all these double chains floating around, and I'm
Mhm.
sure the double chains, once it starts getting colder, they start slowing down.
Mhm.
Those double chains are probably going to start lining up.
They can, or additional single chains could attach to them.
Okay.
So now we have lots of chains attaching to each other in
Spreading
two
out.
dimensions, right?
Oh,
In
cool.
these big sheets
Okay.
structures.
Yeah.
Oh boy,
This is going to get crazy.
I'm not sure we want to draw that one.
That's wild. But if we wanted to, we could just keep drawing those lines and then
We could.
zigzags and all kinds of
We could.
Oh, that'd be nuts.
Yeah. And the key to this is it's two-dimensional in sheets.
Okay.
So it looks like we've got some of those minerals over here.
Absolutely. Two of my favorite to ID. Because we've got these micas. We've got the
Yes.
biotite and the muscovite mica.
Right.
Now, isn't that kind of interesting how they form in sheets?
So you can actually see the sheets of silicate structures in those minerals, right?
So
and you can peel them off.
And if I was to like zoom in, if I had super crazy zoom in powers in my eyes, I
Mhm.
could zoom into a big sheet
Yep.
of all
could.
these continuing side by side by side by side by side.
So actually, when we go in and we peel off layers of this,
Mhm.
what we're doing is we're breaking bonds between sheets.
Oh, cool.
The bonds within that two-dimensional structure are strong because they're sharing those apex oxygens.
Mhm.
But the bonds in between sheets are weak, and that's why we can break them right off in sheets.
So like right now, I'm breaking bonds.
You're breaking bonds, buddy.
So that's something that's pretty awesome to do,
I
right?
think so.
Oh my gosh, I feel like I'm superhuman. How cool.
All right, so we went from the single isolated tetrahedra, which are high temperature, right?
High temperature, yeah.
And things are cooling down,
Things are cooling down, starting
becoming
to
less
slow down.
energetic,
Okay, and we get these
temperature's decreasing.
We get these single chains that are falling
Single
apart on us.
chains, then the double chains,
Oh my gosh.
then we have our sheets of mica.
Okay, which are just a bunch of chains lined up side by side.
Yeah,
And then this is going to get crazier, I'm assuming.
it's going to get crazier because
Oh
you
my
know what
gosh.
happens.
Sheets.
Stack up on top of other sheets.
I don't want to draw that.
No, well, I don't either. And that's the three-dimensional framework. And we have a few minerals that take that structure. So
Okay.
what are those minerals that are three-dimensional framework?
It looks like I got a couple feldspars. Okay. So I've got my calcium, right?
Sodium.
Sodium. Oh, I'm always bad at these. This one's calcium.
That one's calcium.
And then this one is potassium.
You got it.
Cool. Okay. And then, so these are three-dimensional, like, structures. So sheets on top of sheets on top of sheets, with apexes sharing bases sharing bases.
Yeah,
Everybody
all
sharing.
shared.
Oh,
All
it's a
shared.
beautiful community over here.
The way to remember this is that this is a much darker color than this one.
Okay.
So it's going to form around the same time as our mafic minerals.
Okay.
And this is going to form around the same time as our intermediate to our felsic minerals.
Oh, because it's darker, it's going to be closer towards that mafic.
Mm-hmm.
Cool.
Yeah. So we've got the feldspars, and then lastly, we have our
Quartz.
quartz, which
Nice.
is simply SiO2.
So much easier.
Yeah.
And if we did our ratio back again, we'd have one silica to 2 oxygens.
Mhm.
So we've got a lot more silica per our oxygen. So
Yeah.
they're doing a really good job sharing there,
Yeah,
right?
They are. And you can tell we've been using a lot of oxygen as we built these structures. That's why here there's not much oxygen left.
Gotcha.
So 1 to 2, where in olivine it was 1 to 4.
Okay.
Now this 1 to 2, you've got the +4 here and the -4 there. So that's not a charged particle.
Totally balanced.
It is.
Awesome.
All right. So, should we review one time about the
Please.
order that these minerals are forming?
Yeah.
Okay, so we first have olivine,
Okay,
the
our-
single isolated tetrahedra.
Our single tetrahedra, there's a lot of oxygen for a little bit of silica.
Yeah.
Okay? And then we start going down and we get to our pyroxenes.
Yep.
And we're still dark because we've got a little bit of iron and magnesium in there.
Yep,
And these are our single chains.
single chains,
Single chains. So we're starting to share some of the silicon, but we still have a lot of oxygen.
sharing the oxygens.
Sorry,
Yep.
sharing the oxygen, and we're getting more silicon.
Right.
Okay? Then we start having our double chains
Mhm.
together. And this is our amphiboles.
Perfect.
Okay? Still dark, magnesium, iron.
Right.
Okay? Now I got a bunch of double chains lined up. Double chains and single chains start making sheets.
Yep.
Okay? Then the sheets are making our sheet micas.
Right.
Biotite and muscovite mica.
Mm-hmm.
Awesome.
And
Almost
the
there.
biotite is black because it still has the ferromagnesiums in it.
Mm-hmm.
The muscovite is not because now we're dealing with aluminum and potassium.
Oh, so this will form first. We get rid of all of our iron, all of our magnesium,
Yep.
and then it clears up. It kind of lightens up our color.
Uh-huh.
Okay.
Got it.
And then at the same time, once we get past the sheets, we start stacking sheets.
Mhm.
We get three-dimensional.
Mhm.
And then we're starting to form our feldspars.
Mhm.
And we get our dark ones, which is the calcium first.
Uh-huh.
And then we get to our potassium and sodium.
Perfect.
And then when we're in like a perfect sharing environment, we get to our quartz.
Perfect.
Cool.
So the only thing that forms a little wrinkle in this is
Mm.
that this calcium-rich plagioclase feldspar actually forms earlier than the other framework structures form.
Okay.
And it's a little bit to do with the composition, but we know that when we find this calcium-rich labradorite,
Mhm.
we find it in association with the other mafic minerals.
Okay.
So it's up here with these for a reason.
Okay.
That's where we find it.
Gotcha.
And then these are found together in other rocks.
Okay.
So, wow, that was a lot.
Yeah.
Yeah. Well, how do you think they're going to do on this?
I think they're going to do awesomely.
They did well in class. This was a good review for them.
Absolutely.
And we're going to continue on next time with the segment on Bowen's reaction series.
Awesome.
All right.
Cool.
Hey, give everybody a fist bump.
Hey, bye, guys.
See you guys.